Greetings and welcome. This is Dr.BDY Sunil, Associate Professor, Mechanical Engineering Department, Institute of Aeronautical Engineering, Hyderabad. In this session, we will be learning about the problems on moment of inertia and mass moment of inertia. The course outcome of this topic would be calculate moment of inertia and mass moment of inertia of a circular plate, cylinder, cone, and sphere from the first principles. The topic covered would be problems on moment of inertia and mass moment of inertia. The topic learning outcome is understand the concept of moment of inertia and mass moment of inertia involved in practical engineering problems. So this would be our first problem. The problem given is find the moment of inertia of a rectangle shown in figure about centroidal axis and its base axis. So in this problem, in this figure which you can see, there are three axes that is represented. One is the x-axis axis, which is passing through the centroid of the object, and y-y axis that is passing through the centroid of the object, which is the vertical axis. And another axis, the third axis, is the axis AB. So we are going to identify the moment of inertia of this particular rectangle with respect to the centroidal axis and its base axis. So this is the problem given, and we need to identify the moment of inertia. So let us start the problem. The size of the rectangle that is given is height or breadth as 100 mm and the length as 60 mm. So first let us identify the moment of inertia about centroidal axis, that is Ixx or Iyy. As this Ixx and Iyy are considered differently, the moment of inertia of x-axis axis with respect to x-axis axis and with respect to y-y axis are different. We do have the formula for this moment of inertia with respect to x-axis axis as BD cubed by 12. So when you substitute the values, you will be obtaining 60 as the breadth. You can see here, breadth of the rectangle as 60 and depth that is as given as 100. So this would be your D and this would be your B. So we can get the value as BD cubed by 12, 60 into 100 cubed by 12. When you simplify this, you will get the answer as 5 into 10 power 6 millimeter power 4. Millimeter power 4. So this is the moment of inertia of this particular rectangle given with respect to x-axis centroidal axis. Now coming to the moment of inertia with respect to y-y. The formula which we have is dv cubed by 12. So that formula, when you substitute the values, you will be substituting the depth as 100 and breadth as 60 cubed by 12. So when you simplify this, you will be getting the value as 18 into 10 power 5 millimeter power 4. This is the moment of inertia of this particular rectangle with respect to x-axis axis and y-y axis, which are the centroidal axis. Now coming to the moment of inertia about its base AB, about the rectangle's base AB, that is written as IAB. So this formula would be BD cubed by 3. The formula for moment of inertia of rectangle with respect to the base axis would be BD cubed by 3. So when you substitute the values, breadth is 60 and depth is 100 cubed by 3. When you simplify this, you will get the value as 2 into 10 power 7 millimeter power 4. So this is the simple problem where we have identified the moment of inertia of this particular regular section with respect to the centroidal axis as well as the base axis. Now let us go for the complicated section. The moment of inertia that is to be identified for an I section here. Here the I section given, the moment of inertia is needed to find about the centroidal axis XX perpendicular to the web. These are called as the flange. Okay, these are called as the flange and this is called as the web. This is called as the web. So the XX axis should be perpendicular to the web. So in this way, the axis should be. That is the question given here. So the question given is find the moment of inertia of the section shown in figure about the centroidal axis xx perpendicular to breadth. So the sizes, different sizes of this sections are given here as 10 centimeter of total length and 2 centimeter of height of that thing. We can say it as breadth and depth. 2 centimeter as breadth and 10 centimeter as depth, and 6 centimeters, 5 centimeters as breadth and 2 centimeter as depth. For this sort of section, complicated section, the procedure to identify the moment of inertia for compound sections is doing such a way that first we will be identifying the moment of inertia of individual parts, individual sections, right? Here we can divide this given I section into 3 rectangles: base, middle web and top flange. So these 3 rectangles moment of inertia will be identified with respect to the x-axis axis, and that x-axis axis would be the centroidal axis for each and every individual part. Then what we will do is we will consider the moment of inertia of all the centroids, all the individual sections, centroidal axis, and then we will be converting this to the using the parallel axis theorem. We will be converting this moment of inertia of the centroidal axis to the identifying the final moment of inertia of the complete section. So that is the procedure which we will adopt. So if you see here, we have taken the reference axis and as well as the individual sections. We have divided the individual sections. See, this is section 1 rectangle, second rectangle and third rectangle, and the distances has been identified here with respect to the axis which we have considered. This is the origin which is taken, and this is the y-axis, and this is the x-axis which we are considering. And with respect to this x and y-axis, we will be identifying the distances of the centroid. If you observe carefully, this I section is symmetrical about the centroidal axis here passing through this. So we can consider this as yy. And centroids will be lying on the symmetrical axis. Okay, so directly we can consider the symmetrical axis and we can take the centroids of each individual rectangles, and from the axis that are passing through these centroids, we can consider the values of the moment of inertia. And how we have identified the centroids here, you can observe. For this first section, we have considered the moment of centroid of this. We have identified the centroid of this particular rectangle 1 as 1 centimeter from the reference axis, that is x. Then centroid of the second thing as 7 centimeter from the reference axis. Actually, this is at a length of 10 centimeters, but the reference axis is at a distance from the base. So this is 5 centimeter plus 2 centimeter. That will come to 7 centimeter. Similarly, the centroid of this top flange would be, this is 1 centimeter. Okay, and totally from here it is 10 centimeter and 2 centimeter, that is 12 centimeter. So complete y3 can be obtained as 13 centimeter. So in this way we have identified the centroids of the different individual rectangles. Now what we do is we will be identifying the moment of inertia of these individual rectangles through the centroidal axis. The procedure is shown here. The given section is symmetrical about yy axis and its centroid will be on yy axis. Divide the given section into 3 rectangles. So we will be identifying the areas and values of the centroids distances from the reference axis like this. Area of first rectangle is A1, that can be obtained as 5 into 2, which is 10 centimeters square. Whereas the distance of centroid from the reference axis is y1 is equal to 1 centimeter. Coming to the area of the second rectangle, which is 10 into 2, that is equal to 20 centimeters square, and y2 is equal to 7 centimeter. Then coming to area of rectangle 3, which is 10 into 2, that is 20 centimeters square, and the distance of centroid from the reference axis y3 is 13 centimeter. So overall, if we identify the centroid of the total figure, that would be y bar is equal to a1 y1 plus a2 y2 plus a3 y3 by a1 plus a2 plus a3. So with this, we can simply substitute the values of A areas and the y-intercepts here. So we can obtain 10 into 1 plus 20 into 7 plus 20 into 13 by 10 plus 20 plus 20. That gives the value as 8.2 centimeter. Now, identifying the moment of inertia of rectangle 1, individual sections moment of inertias, we can get the value as Ix1. Ix1, where Ix1 is the moment of inertia of rectangle 1 with respect to x-axis. That is equal to Ig1 plus A1 H1 square, where A1 we know the area of the rectangle and H1 square is the value of the distance of this reference axis, which is x-axis, to the centroidal axis. The distance of reference axis to the centroidal axis that we will be calculating from the figure. So the values can be obtained as B1 D1 cube by 12, which is the moment of inertia of the rectangle with respect to the centroidal axis, plus A1 H1 square, where H1 value would be 7.2. When you simplify this equation, you will get the value of Ix1 as 521.73 centimeter power 4. Now, the moment of inertia of rectangle 2, it can be represented as Ix2, that is moment of inertia of rectangle 2 with respect to the x-axis, and that can be given as with the equation Ig2 plus A2 H2 square. Now applying the formula B2 D2 cube by 12 plus 20 into 12 square. When you simplify this, you will get the value as 195.47 centimeter power 4. Now the moment of inertia of rectangle 3. So Ix3 is equal to Ig3 plus A3H3 square. That is equal to B3 D3 cube by 12 plus A3H3 square. That is equal to 10 into 2 cube by 12 plus 20 into 4.8 square, which gives the value as 467.47 centimeter power 4. Now the moment of inertia about centroidal axis XX. It is identified as Ix is equal to Ix1 plus Ix2 plus Ix3. That means we are adding all the moment of inertias of individual sections or individual rectangles to obtain the final moment of inertia with respect to the reference XX axis. When you add all these things, 521.73 plus 195.47 plus 467.47, you will obtain the value of moment of inertia as 1184.67 centimeter power 4. This is your moment of inertia for the given I section. Now let us do the moment of inertia or identify the moment of inertia of a solid. This is also called as the mass moment of inertia. There is a cube given of side 400 millimeter as shown in figure. It has the mass density of 2000 kg per meter cube. Now the question given is find out the mass moment of inertia of the cube about its centroidal axis parallel to one of its side and one of its edge. Okay, one of its side. The given cube's one of sides parallel and the edges parallel. Let us solve the problem. Here you can observe the volume of the cube is A cube. The value of A, the side is given as 0.4 meter. So the volume of the cube can be considered as A cube. So that will be obtained as 0.4 cube. The value is 0.064 meter. Then mass of the cube can be identified as M is equal to density into volume. So the density value is given as 2000 kg per meter cube. So we can substitute the values 2000 into 0.064, that can be obtained as 128 kg. Now mass moment of inertia or the moment of inertia about centroidal axis. Centroidal axis can be obtained as Iyy is equal to M into A square plus A square by 12. This is the formula which we have. So when we substitute the values, we will be obtaining 128 into 0.4 square plus 0.4 square by 12. simplify this, you will get the value as 3.413 kg per kg meter square. Now coming to the second case with respect to the edges. Moment of inertia about the edge A dash. Here you can observe this is the moment of inertia we are calculating with respect to the edge of the cube. Edge of the cube. Side, just now we have calculated the moment of inertia along the centroidal axis. Now we are going to calculate the moment of inertia with respect to the edge. From parallel axis theorem, we can say that IAA dash is equal to IG plus MH square. So we can obtain the value as IYY plus MH square, where H square is equal to A by 2 square plus A by 2 square. From the figure, we can obtain this A by 2 square. Then 0.2 square plus 0.2 square, that is equal to 0.08 meter square. So here we can say IAA dash is equal to 3.413 plus 128 into 0.08. So we can obtain the value by simplifying this equation as 13.653 kg meter square. So this is how we are going to calculate the mass moment of inertia applying the equations that we have. This concludes the session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.